Welcome to Everyday Mathematics. Today we are still on the 2022 Columbia University Integration B qualifying round, and we're shifting forward to part 3 of the session. We'll be looking at problem number 21 in that series, problem number 22, problem number 23, problem number 24, 25, 26, 27, 28, and 29. So without much ado, we'll move forward to solving this problem. But even before I proceed into that session, I'd like to encourage our new visitors. If you not subscribe to our channel, we do really encourage you to consider subscribing to our channel. If you like what you're seeing, we do encourage you to consider liking our video and also do share if you find our content worth sharing. So without much ado, let us proceed into the solution phase of this video. Number 21, which is the indefinite integral of sine of cosine of sine of x times sine of x times cosine of x. So this is an interesting problem, and we would have to begin from the very end here, right? So our problem becomes, this here is a derivative, this part here is a derivative of sine of x, so this is the same as sine of cosine of sine of x times sine of x times the derivative of sine of x. So it's interesting because what we're seeing here is that this part here is the derivative of the negative cosine of sine of x, right? So that implies that our problem is sine of cosine of sine of x times the derivative of cosine of sine of x. So what we can also see is that this entire part here is actually the derivative of negative of cosine, actually it's positive of cosine of x, right? So in other words, we are integrating the derivative of cosine of sine of x, right? Let's just make sure we are right here. The sole reason is because we do have this negative here, and then when you're differentiating negative of cosine, the two negative cancel, so this becomes a plus. And so our answer here becomes cosine of sine of x plus the integration constant. And that is our answer. So on to problem number 22, the definite integral from x equals to 0 to x equals to 1 of the square root of 1 minus x squared. The most easy part of this is to just draw out what this function looks like, and it's like that. So from 0 to 1, and this is just a quadrant of a circle of radius 1. So In other words, 0 to 1 square root of 1 minus x squared dx is the same as a quarter times the area of the circle, which is pi times 1 squared. So this is pi over 4, right? And that is it. Could also say let x be equal to sine theta, such that dx d theta is equals to cos theta. And so when x equals to 0, theta equals to arc sine of 0, which is 0. When x equals to 1, theta is equals to arc sine of 1, which is pi over 2. So we have 0 pi over 2 square root of 1 minus sine theta times cosine theta d theta from this part here. So we have 0 pi over 2. This is same as cosine theta in that interval. So we have cosine square theta. And so this is the same as half 0 pi over 2 cosine 2 theta plus 1. Right? And so we do have half 0 to pi over 2 cosine 2 theta plus 1, which is a half. With that, a half sine 2 theta plus theta, 0 pi over 2. So this is the same as a half sine pi plus pi over 2 minus a half sine 0 minus 0. This is 0, this is 0, this is 0. And so we have a half times pi over 2, which is pi over 4. So we do have two methods for us that just solidifies our initial assertion, where we said the integral from x equals to 0 to x equals to 1 of the square root of x squared is pi over 4. Problem number 23, which is the indefinite integral of the natural logarithm of 5x over x times the natural logarithm of x. So here what we'll do is we could re-express this as the natural logarithm of 5 plus the natural logarithm of x. So let's just put bracket over x, natural logarithm of x. And this we're using the rules of logarithm, where if you have log of AB, that's the same as natural logarithm of A plus natural logarithm of B. So we're using this relationship to separate the numerator. Now we can say also let u be equal to the natural logarithm of x, and so du dx is equals to 1 over x, and so du can be used to substitute for dx over x, an important point for us. Therefore, the integral of natural logarithm of 5 plus the natural logarithm of x over natural logarithm of x, and this we can bunch it together, so we have dx over x is the same as the natural logarithm of 5, which is a constant, plus u, which we pick from here, over u, and this is du. So this happens to be natural logarithm of 5 over u plus 1. So integrating this and integrating this separately, we get natural logarithm of 5 times the natural logarithm of u plus u plus the integration constant. So that's the answer. But we said u equals to natural logarithm of x, right? So this is the substitution that we did. That implies that our answer now becomes natural logarithm of 5 times natural logarithm of x plus natural logarithm of x plus c, the integration constant. And that happens to be our answer. So next, problem number 24, the indefinite integral of the natural logarithm of x squared plus 4. So how I may be able to solve this is I could express it in this form, right? And this is with the assumption that there's a hidden 1 here, there's a hidden 1 there. And then we can go ahead and use integration by parts, where if you have a product of a function v and the derivative of function u, when you integrate that, you get uv minus u, the integral of u minus the derivative of function v, right? So this is important. With that in mind, we now have x, natural logarithm of x squared plus 4 minus, then we have x times the derivative of the natural logarithm of x squared plus 4, right? Which is x natural logarithm of x squared plus 4 minus x times derivative of this over x squared plus 4. So which is x, the natural logarithm of x squared plus 4 minus 2 x squared over x squared plus 4. Right? So since we've come to a point where we have x squared plus 4 minus 2 x squared over x squared plus 4, this can also be expressed as 2 x squared plus 4 over x squared plus 4 minus 4x squared plus 4. So this and that cancel. So essentially we have x plus 4 minus 2, the x plus 2, 4 over x squared plus 4. Okay. So this is easy. This part here, we can so with this we need to solve this. This will solve to 2x, but this will be interesting because we say let x be equal to 2 tan theta. So dx with theta is equal to 2 sec squared theta. And so for dx is times 2 sec squared theta d theta over 4 tan squared theta plus 4, and the 4 can go out so that this would cancel, and we have 2 sec squared theta over sec squared theta, which is 2 integral of 1, which is 2 theta plus c. Okay, so but we said let x equal to 2 tan theta, meaning that x over 2 is equal to tan theta, and therefore theta is equals to arctangent of x over 2. Therefore, the integral 4x squared plus 4 dx is equals to 2 theta plus c, which is 2 arctangent of x over 2 plus c. Initial integral that we had in mind, which was essentially the integral of the natural logarithm of x squared plus 4 is equal to x, natural logarithm of x squared plus 4 minus 2x, and then we had plus 2, so we have 4 arctangent of x over 2 plus c. And that, ladies and gentlemen, is our answer. So the next problem, problem number 25, which I think is a trick problem, the integral of e to the x over sine of square root of x plus cosine of the square root of x, and that is in the z. So we're integrating with respect to z, but we have x all over. My thought is this would be e to the x sine square root of x plus cosine square root of x z plus c. I don't know if you have an alternative solution. Please reach to us and let us know. But we think that this was the bigger trick in the entire question. So problem number 26 happens to be the indefinite integral of the cosine of root of x. So the quickest inclination is for us to substitute for square root of x. And what we do is we say let u be equal to square root of x. And so x squared is going to be equal to x. And so if we differentiate with respect to x, we have du dx being equal to 1. And what that means that 2u du can be used to substitute for dx. So that's an important step. And so our integral in the x domain becomes as follows in the u domain, right? Which is equals to 2u cosine of u. And cosine of u can be expressed as the derivative of sine of u, right? So that if we use integration by parts where we have a product of a function v and the derivative of a function capital U, when we integrate that, we have capital U times capital V minus the integral of capital U times the derivative of function V. So using that, our problem now becomes 2u sine of u, this is uv, minus 2 sine of u times the derivative of u, which is 1, and so that's where we are. So since we have 2u sine of u minus the integral of 2 sine u, this becomes 2u sine of u plus 2 cosine of u plus the integration constant c. But we say that mu is equal to square root of x, right? Which means that our integral, original integral, is equal to 2 square root of x sine square root of x plus 2 cosine square root of x plus c. That is our answer. Next is problem number 27, which is the definite integral rather from x equals to 0 to x equals to pi of e to the x plus cosine of x all over e to the x plus sine of x. Now this problem is very simple. So this is the same as integral from x equals to 0 to x equals to pi of the derivative of e to the x plus sine x over e to the x plus sine of x. And since we know that if you have an integral where the numerator of the integrand is the derivative of the denominator, that becomes natural logarithm of fx when integrated plus c. So knowing that, then it means that we do have a natural logarithm of e to the x plus sine of x 0 to pi. And since this is continuous within this, we can now say this is the same as ln of e to the pi plus sine of pi minus ln of e to the 0 plus sine of 0. So this goes to 0, this goes to 1, this goes to 0, right? So we have ln of e pi minus ln of 1, this goes to 0, and so this becomes pi ln of e, and ln of e is to 1, so the answer is pi. And therefore, what that means is our integral from 0 to pi of e to the x plus cosine of x over e to the x plus sine of x is equal to pi. That's our answer. So our next problem is the definite integral from x equals to pi over 3 to x equals to 5 pi over 6 of the square root of cosec of x minus sine of x. So this is, let's re-express cosec of x as 1 over sine of x. So integral from x equals to pi over 3 to 5 pi over 6 of the square root of 1 over sine of x minus sine of x, right? And that becomes square root of x over the square root of sine of x. So this becomes sine of x square root sine of x. And what we see is our numerator becomes the absolute value of cosine of x, right, over square root of sine of x. And so if our problem is as follows, then it means that we have x times cosine of x, right? Where sine of x equals to -1 when cosine of x is less than 0, and +1 when cosine of x is greater equals to 0, right? So with that in mind, it means that we know when x equals to pi over 2 is when cosine of x crosses to the negative domain. So we can split this into two separate integrals. Cosine of x, So that's our problem becomes pi over 3 to pi over 2. Cosine of x is going to remain there in the numerator. And then negative from pi over 2 to 5 pi over 6 we have. So this sign becomes negative in this domain. Right? And what that means is that if we do have pi over 3 to pi over 2 cosine of x square root of sine of x minus pi over 2 to 5 pi over 6 cosine of x over square root of sine of x. This essentially means that we have pi over 3 to pi over 2, the derivative of sine of x in the numerator over square root of sine of x minus 5 pi over 6. I can pretty much reverse the limits here, but I'll just keep it as it is right now so that we have, in essence, 2 square root of sine of x pi over 3 pi over 2 minus 2 square root sine of x pi over 2 5 pi over 6. So this becomes 2 square root of sine of pi over 2 minus 2 square root sine of pi over 3 minus 2 square root of sine of 5 pi over 6 minus 2 square root sine of pi over 2. So this goes to 1, this goes to 1, this goes to 2 square root of root 3 over 2, and this goes to 2 times 1 over root 2. Okay, so in essence we do have 2 minus 2 fourth root of 3 over root 2 minus 2 minus 2. So this and this means that we do have a 4 because we're adding to this, and then we have root 2 fourth root of 3 minus root 2. Therefore, our integral from pi over 3 to 5 pi over 6 of cosec of x minus sine of x is equals to 4 minus root 2 times the fourth root of 3 minus root 2. And that is our answer. So problem number 29, which happens to be the last problem, is the indefinite integral of 2x times the arctangent of x. And so what I can begin by saying is 2x is the same as the derivative of x squared times the arctangent of x. So I'll just choose to write arctangent in this format. This is how I'm very comfortable writing it. And from here, I can use integration by parts, where we say if we have function v times the derivative of function u, that's the same as uv minus the integral of function u times the derivative of function v, right? And so our u happens to be x squared, our v happens to arctangent of x, therefore our uv is x squared times the arctangent of x minus u being x squared, so we have x squared times the derivative of arctangent of x is 1 over x squared. So for those of you who need explanation on this, we can do that, but it's it's something that is straightforward. You know what? Maybe let's just go ahead and show how to do that. So if you have a function u being equal to the arctangent of x, that means that tangent of u is equals to x. Therefore, sec squared u du dx is equals to 1, derivative of that, and therefore du dx is equals to 1 over sec squared u, which is squared of u, which is the same as 1 over 1 plus x squared. And that is how you would be able to show that. So it's a straightforward thing. Anyway, back to our problem. So this becomes now x squared arctangent of x minus x squared over 1 plus x squared dx, meaning that this is the same as x squared plus 1 minus 1 over x squared plus 1. So we'd see that we can say x squared minus x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. Right? And so we see this and that would cancel, so that we do have x squared arctangent of x minus 1 minus 1 over x squared plus 1. So the integral of 1 is x. The integral of this, we saw that the derivative of arctangent of x is 1 over x squared. So the integral of 1 over x squared plus 1 is the arctangent of x. So our answer now becomes x negative 1 x minus x negative and negative. We have plus the arctangent of x plus the integration constant. Therefore, our integral of 2x, the arctangent of x, is equal to x squared times the arctangent of x minus x plus the arctangent of x plus the integration constant. And that, ladies and gentlemen, happens to be our answer. So that brings us to the end of this video. If you liked what you saw here, we do really encourage you to subscribe to our channel. If you like, you could share to someone who might benefit from our video. We do enjoy solving these problems. It's been an absolute pleasure hanging out with you this time around. Until next time, bye-bye.